Welcome to Homework Lib.
Hi, so over here, in order to know where the electric field and the electric potential are going to be zero, we're going to help ourselves with a little sketch of where this point should be. So for example, if we choose a point outside of X, we're going to see that the electric potential due to charge 1, since the charge is negative, it is going to be attractive, so the potential will be pointing towards the left. And since the second charge is positive, then the potential due to that charge would be pointing towards the right. So we know that the distance over here from charge 2 to this certain point is going to be equal to r, and the distance from charge 1 to the same point is going to be equal to r plus 3. Now, what we need to do is solve for r for both of the different equations. First of all, we know that the electric potential is going to be equal to the sum of the electric potentials due to all of the charges present in our system. In this case, from the first charge, we're going to have k times minus 3q divided by distance squared, in this case, r plus 3 squared, plus k times the charge of the second charge, 2q, now positive, divided by r squared. The potential needs to be equal to 0, so what we can do is equate these equations, and we're going to get 2kq over r squared is going to be equal to 3 times kq over r plus 3 squared. Let's separate these equations. We're going to get r plus 3 squared is going to be r squared plus 6r plus 9. This is going to be multiplied by 2kq, and this is going to be equal to rkq times r squared. Putting things together, we're going to get, let's collect the 3kq times r squared towards the left. So we would get r squared multiplied by 2kq minus 3 times kq plus 6r kq multiplied by 2 times kq plus 9 times 2 times kq. All of this needs to be equal to 0. Now let's factorize the kq factor. We're going to end up with minus r squared plus 12r plus 18. And this can only be 0 if whatever we have inside the parentheses is equal to 0. So the solution for r comes from solving minus r squared plus 12r plus 18 equals to 0, which gives us two different solutions, r1 and r2. The two solutions in this case are 6 minus 3 times square root of 6 and 3 times 2 plus square root of 6. Notice that the first one is going to be negative, so this is lower than 0, so this is not going to be a valid solution since we have by definition that the distance is going to be positive, and the second one is approximately equal to 13.34847 meters in this case, because the units of distance that we have in this problem are going to be meters. So now that we know the distance over here, we can say that r is equal to 13.34847. Thus, the position on x is going to be that value plus 3. So the result would be 16.34847 meters. So at that position in the x-axis, the field is going to be 0, and the potential is also going to be 0. You can verify this simply by plugging in the values. We can calculate it, for example, just to verify that the electric field indeed is going to be equal to 0. Electric field due to charge 1 is going to be equal to k times the charge 1, that is minus 3 q, divided by the distance squared that we said that was 16.34847 squared. Of course, this is going to be on the I-axis, plus the one coming from the second charge, that is going to be 2kq divided by, in this case, 13.34847 squared. So what we need to compare is this guy with a negative value plus the other one with a negative value, which the positive one, of course, this again is going to be in the I direction. This is going to be 1.12245 times 10 to the minus 2. And on the other side, we're going to get exactly the same number, 45 times 10 to the minus 2, kq, but with the opposite sign. So this verifies that indeed the electric field is also going to be 0 at that position. So just to recap, first we sketched what would be the direction of the electric field to know if the position should be in between the two charges, to the right or to the left. In this case, to the right seemed the most sensible choice. If you do it towards the left, you're going to find a very similar result. And from here, on the x-axis, we employed the potential and the sum of the individual potentials to find an equation solving for r, the distance. We noticed that the distance in between charge 1 and the hypothetical point was r plus 3, and in between charge 2 and the hypothetical point, we label it as r directly. Solving the equation, we got two results. One was negative, the other one was positive. We keep the positive result because that is the one that has physical meaning. And we verified with the electric field that the direction is correct. So that would be all. Thank you very much and have a good one.